Hi everybody, this is Mr. Short. Today we're going to be learning about orbital notation diagrams. Now remember, we're in section 1.2, and in section 1.2 we learn about different ways to represent electrons. Before we get into orbital notation diagrams, let's take a look at some different ways that we know to represent electrons. This is an example of sulfur. Sulfur, because it's element 16, would have the complete electron configuration 1s2, 2s2, 2p6, 3s2, 3p4. And you can see that the sum of the exponents adds up to 16 because those exponents are the electrons. Now this is the complete configuration, and then we can turn that complete configuration into a Bohr atomic model. So here are some of the things that we should understand at this point. The 1s, 2s, 3s, and another 3 here tells us the energy level. First energy level, second energy level, third energy level. The exponents are the electrons that are on those energy levels. And in particular, this has 2 plus 4 is 6 valence electrons on the third energy level. 1, 2, 3, 4, 5, 6 valence electrons. This is a Lewis structure over here, and this is a simplified way that we can represent electrons. It only shows the 6 valence electrons. And if we took a look at the periodic table, sulfur would be found in main group 6, telling us that it does have 6 valence electrons. Today, though, we're going to be learning about another representation called an orbital notation diagram. I think it's best to start out by taking a look at a couple of orbital notation diagrams so that you can see what they look like, and then we're going to work backwards and understand what all of this information means. So let's get started. Okay. If we want to represent the orbital notation diagram for sodium, which is element 11, we're going to need 11 arrows that go into these different orbitals right here. So it's going to look like this. I'll use some language now that I'm going to use later in this screencast. We'll go single, single, single with the same spin, and then double, 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 each with the opposite spin. Now, we've got one last electron to represent, and it goes like that. Now, if we count up those arrows, you'll see that there are 11 arrows. Those 11 arrows are the 11 electrons that we're representing in this orbital notation diagram. Likewise, here's sulfur. Sulfur is going to look like this with its orbital notation diagram. So we go single, 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 before double, double, double with opposite spins. Now, inside the 3p sublevel, we're going to have a total of 4 electrons, and it goes single, 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 before double. So if we were to count up these arrows, what we would see is that we have 16 arrows representing the 16 electrons that would be inside sulfur. So now what we're going to do is we're going to go back and we're going to get a better understanding for why we write orbital notation diagrams this way, according to 3 rules which are called Aufbau principle, Hund's rule, and Pauli exclusion principle, and we'll understand what all of the arrows mean and what all of the dashed lines mean. Okay, first we have to start out with this statement. In the order of electron configuration, which is something that we're familiar with, electrons that are farther to the left in the electron configuration have less energy than those that are farther to the right. So I'm going to write a note right here on this sequence, and I'm going to put low energy over here on the left-hand side, and I'm going to put high energy over here on the right-hand side. So what this means is that when we write electron configurations and we start out with 1s2, those would be very low energy electrons. And as we move further to the right, the further to the right that we move, the electrons gain more and more and more energy. Let's take a look at what this means in an orbital notation diagram. Now remember, we've got this example of sulfur right here, and we've also got this example of sulfur right here. I'm going to scroll up, and you're going to see exactly the same orbital notation diagram for sulfur that we had on the previous page. But shown in a little bit different format, we've got those electrons in the orbital notation spread out on an energy diagram. Notice that we have energy on the y-axis right here. Because energy is on the y-axis, it tells us that these 1s2 electrons that are right here must be very low energy, and that these 3p4 electrons that are right here must have more energy than any of the other electrons that are in these sublevels and orbitals. Okay, let's think a little bit more about that. These 1s2 electrons right here are the lowest energy, but because these two electrons are at exactly the same height on the y-axis, these must have equal amounts of energy. Likewise, these two electrons have equal amounts of energy, and each one of these electrons has more energy than these electrons right here. And we could go up the ladder and say exactly the same thing about all of these. These 6 have equal energy and more than these 4, just like these 4 have equal energy and more than all of these remaining electrons. So remember, the further to the left you are in the sequence, the lower energy the electrons are, and the further to the right in the sequence, the higher energy the electrons are. That's the meaning of this statement that's right over here. And in general, what that means is that electrons that are closer to the nucleus have less energy than those that are farther from the nucleus. Okay, that's a broad general statement, but it relates back to this energy sequence right now. So now at this point, what we're learning is that not only is this the order that we fill electrons into the electron configuration, but we also know that electrons that are further to the left in this sequence are lower energy, and those further to the right are higher energy. Okay, so now we ask the question, what are orbitals? After all, this is called an orbital notation diagram. So electrons, which are the arrows, electrons are found in orbitals. Those orbitals are located in sublevels, which are on energy levels. We also know that each orbital can hold at most 2 electrons, and those 2 electrons have opposite spin. Let me change the text color. So this is they have opposite spin. So if we take a look up here, I can count a certain number of orbitals in this orbital notation diagram for sulfur. I can count 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. The orbitals are the dashed line in an orbital notation diagram. Also in this type of diagram, the arrows represent the electrons, and what the direction of the arrow means is the direction that the electron will spin around its axis. If it's an up-pointing electron, what that means is it's spinning one direction, and if it's a down-pointing electron, that means it's spinning exactly the opposite direction. So again, this statement says electrons are found in orbitals, orbitals are located in sublevels, sublevels are located on energy levels, and we also know that each orbital can hold at most 2 electrons that have opposite spins. The spins are represented with the directions of the arrows. So this should be a chart that we're familiar with. Remember, the S's, P's, D's, and F's are called sublevels. We should also know the maximum number of electrons that can be held in each sublevel. I'm going to give you a minute to fill in this portion. I want you to hit pause, and then when you're done filling it in, come back to the video. Okay, the numbers that go in these spots are 2, that's the most electrons that can fit in an S sublevel, 6, 10, and 14. Remember, it's a sequence. It starts with 2, and you keep adding 4. 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 is 14. It also relates to structure and organization on the periodic table, and you should be able to spot the S, P, D, and F sublevels on the periodic table. So now we might ask the question, well, if each orbital can hold 2 electrons, and the S sublevel can hold 2 electrons, then how many orbitals are in an S sublevel? That answer is 1, and we can see that right up here. See how every time we write S, we put one dashed line, 1 orbital after it. Here's an S, we put 1 orbital after it. Here's an S, we put 1 orbital after it, and that 1 orbital can hold 2 electrons with opposite spins. We might also ask the question, well, if we're talking about P sublevels, and P sublevels can hold 6 electrons, and each orbital can hold 2 electrons at most, then how many orbitals are in the P sublevel? And the answer, of course, is 3. And we can see that in these orbital notation diagrams. See how every time that we write P, we write 1, 2, 3 orbitals after it. P, 1, 2, 3 orbitals after it. P, 1, 2, 3 orbitals after it. Okay. So you might predict that if we were to write a D sublevel, afterwards we would write 5 dashed lines, 5 orbitals, and if we wrote an F sublevel, we would write 7 dashed lines, 7 orbitals. So now we're going to talk about a series of 3 rules which are called Aufbau principle, Hund's rule, and Pauli exclusion principle. Each one of these describes the reason that we fill the orbitals the way that we do. Aufbau principle says this. It says that electrons will fill the available orbitals from lowest energy to highest energy. Okay, so right here we're going to write lowest energy to highest energy. And if you take a look up here, remember, we've always written electron configurations starting here and then letting remaining electrons spill over here, completely fill this up, then let any remaining electrons spill over here, and so on and so forth. So what we say is we always start from the left and work to the right. Or said according to Aufbau principle, we always start by filling in the lowest energy orbitals first, and then progressing towards the higher energy orbitals second. Okay, I'm going to hit pause and make another video to represent Hund's rule, Pauli exclusion principle, and then do these 3 examples down below.